Okay, Assalamualaikum and good day, everyone. So we continue our lecture, okay, on the new topic, okay, which is interconnect. So if you go to your textbooks, okay, it is on the page of 211, page 211. Title is interconnect, chapter 6 of the textbooks, right? So we go to the lecture note or lecture slide. So we will discuss a bit on the brief introduction about the interconnect, right? And then after that, we will see on the aspect of resistance, okay, capacitance, and also the element of two, so resistance and capacitance delay, okay, RC delay, okay. So interconnect, sometimes people call wire, it's actually wire. So why we call it interconnect? Because in chip design, is the using of interconnect is more specific or more appropriate for the SI designer or chip designer. Wire is something like, physical wires, and people will think about physical wires, and that's why they use interconnect. Right. So after that, we will discuss about the effect of crosstalk. Okay, crosstalk is actually unwanted lah. It's unwanted effect of the interconnect. Actually, there's actually a side effect of interconnect, but we cannot, run away from it. And we have to discuss the effect of the crosstalk in order for us to design a chip in reduce, okay, or improve the crosstalk effect. Okay, we try to minimize the crosstalk effect. Okay, so that's why we need to learn what is actually crosstalk and what are the effect on the overall chip performance, right? And then we will discuss about wire engineering or interconnect engineering. How do we design interconnect in our chip? Okay, because as we discussed on our previous lecture, okay, the current challenge is not actually on the transistor, because the number of transistors doubling every 2 years or every 18 months, as predicted by the most, or even more than that, okay, the number of transistors. So this is because of the application, okay, because from day to day, we want the application to be more advanced, okay, more function, okay. So when that, for example, we have now we have a mobile phone with AI function, for example, artificial intelligence function. We want our camera is able to detect our face or others' face smile, and then the camera will automatically snap for you without you asking others to get ready and then count 1, 2, 3, and then it will do capture for you. And we have a different function. For example, you wave your hand and then the camera will snap the photo, or you use your voice and then the camera will snap the photo without you physically touch the screen. So that's actually a function, a lot of function. We can also implement other function in our phone. So a lot of function means that a lot of processing capability, and processing capability related to our processor. Okay, so means that our processor need to be intelligent enough, need to be sophisticated enough to support the demanding application, okay, demanding what we call sophisticated operation, complex operation, okay, including the AI processing capability and so on. And to have a complex or very good or very high performance processor on a single chip, we need to have a lot of transistors, a lot of capability in terms of the processor. Okay, that's actually translate in terms of the hardware or element required, okay, for a transistor. And same as memory, okay, the number of memory, the capacity of memory is now getting what we call as requirement, okay, not just support, requirement. The more the memory, the better, or the performance of the application, okay, we can do a lot, okay. Even your computer or your phone quickly run out of space because of a lot of application. You have WhatsApp application, for example, and you need to clear it every day, for example. That's actually related with the memory capacity in your phone, and relate actually to the hardware or device in your processor, which is actually requires more transistors for more application. And actually, that actually requires more wiring, or more complex wiring or interconnect between the transistors, because we have a lot of transistors there. We have learned this about the physical chip floor planning. We have discussed, and we can see, we already see the what we call the complexity of wiring there. Okay, example of the Intel Itanium processor. Okay, if you can recall that, and then you see the complexity in terms of wiring. Okay, and we even have actually multiple layers of chip. Okay, 7 layers, 6 layers of Intel processor chip. We have discussed this. So the number of layers is actually to avoid the ratio of complexity in terms of wiring and in terms of the number of transistors. Like human, right? We as human, when we stay in city, okay, the land area is very expensive, and what people do, people will build up an apartment, condominium, and so on, to occupy as much as possible people in that particular area. So they have a stack, multiple stories of building. Right. So, and then after we see the wire engineering, we will also see repeaters. Repeaters is actually a way to reduce, not to overcome, only reduce the effect of low signal of data. Our data we can make it always strength. The strength is always up to the optimum one by having a repeaters at a certain point. Okay, to make it sustain and maintain. Right, and then we will discuss about crosstalk control. How do we control the crosstalk? And towards the end, we will also discuss about regenerators. Right. Okay, so before we go further into detail, I give you some time to read before we continue. So try to read this. Then we shall discuss. I give you about 2 minutes to read. All right. Okay, hopefully everyone has read until the end. Okay, so before I forgot, here we have the attendance. So maybe I can share first. In the attendance, I need you all to respond. Okay, you all to respond in terms of class activity. You write here online or face-to-face class. and under the answer, you write the answer. What's your preference? Okay, for example, face to face, and then you put dash, and then you give your justification. Okay, there's actually there are pros and cons of having class either online and face to face. Okay. So I just want to get response from you all. All of you need to fill in, and then you submit. Right. So I repeat. So the class activity you just write online or F to F or face to face, and then here the answer you answer your preferences, either your preference, either online or face to face, and then you give your justification why. Right? Thank you. So I give you the link in the chat box. Okay. Okay, I already shared to you. Okay. So this will be considered as attendance. All right. While you fill in the form, so let's continue our reading before we continue discussion on this.
Sir.
Yeah, is anyone talking?
Saya.
Yeah, Haris Mukri, can you make it louder?
Okay, sir, saya nak tanya kalau kita buat kelas online kan, kita saya boleh jumpa doktor ke kalau nak discuss luar?
Yeah. Yes, you can come to my room. In the morning, 8 a.m. until 1 a.m. I'm in my room. You can come and see me.
Okay, doctor, thank you.
Okay. So, yeah, inshallah we will do face-to-face at least once to see you all and to discuss. Okay, but next week I plan to have an face-to-face class so at least we can see each other. All right, thank you for the question.
Sir, sorry. So for this next week is face-to-face and following week is online or how, sir?
Yeah, so beginning from next week, that's my plan. Beginning from next week, we will have a face-to-face.
Okay, so then the following weeks also face-to-face.
Yeah, we'll see the what we call
based on the polls. Based on the polls by student. Okay.
Yeah. We'll see it. Yeah, we'll consider all the input from you all. Okay. Okay, thank you.
Doctor, so if majority they choose online, then we will continue with online, right?
I will decide.
Okay.
All right. Thank you. Okay, thank you everyone for the response. All right, so we go back to our syllabus or section, right? Okay, so wires link transistors together. So that's actually the purpose or the function of a transistor. The wire, sorry. The wires link. So that's actually the main purpose of wires. It link transistors together. So for example, you have clock, okay, from the source, so from the main source. It is impossible if you don't have wire to interconnect from the main source of the clock to the clocking element inside your chip. So that's impossible. Okay, so that's why we need wires to do the interconnection. So it will transfer the main clock source to the clocking element throughout your chip. So you have done your lab, and you also see how the wires, okay, do the interconnection, okay, between the main clock source and to the all the clock element. Okay. We also have different types of clock distribution network. So please read that one on your own, okay. And we will have also discussion on it by the group presentation. So wires link transistors together, called interconnect, okay, and then we call it wires interconnect, and play a major role in the performance of modern system, right? So that's actually brief definition or application of wires in our chip. So in the early days of VLSI, means that a long time ago, okay, transistors were relatively slow. Okay, means that transistor not as fast as today, okay, because of the technology during that time. The wires were wide, okay, during that time wires were wide and thick, okay, and thus had low resistance. So this is, if you can imagine, a wire like a pipe, okay, which water flow through the pipe, okay. So if the pipe has bigger hole, then lots of air, water can get in at a time, okay. But if the pipe is smaller, and then the water cannot go much as compared to the bigger one. So same as the electronic wire interconnect, okay. So the wider and the thicker the wire, the lower the resistance. Okay. Under those circumstances, wire could be treated as ideal equal potential nodes with lump capacity. So during that time, wires not a challenge to do the wiring, because the transistor size during that time is bigger, and also is not faster as today. Okay, when the transistor getting faster, the switching getting faster, and then our wires need to support that features. At the same time, today, in modern process VLSI today, transistor switch much faster, okay, and the number of transistors also a lot. Okay, that's actually the challenge. Meanwhile, wires have become narrower. This is actually the challenge. And because we want our chip to be as small as possible, lightweight as possible, okay, means we want to reduce the area of our die so that we can optimize the number of die per wafer, and then we can have what we call more product, okay, yield, we call yield, more yield per silicon wafer. Then we try to reduce the number of, to increase the number of die per wafer, okay, try to increase. Driving up their resistance to that point, then in many signal paths, so the wire RC delay exceed the gate delay. So this is actually the scenario, okay, RC delay, okay, RC delay means that the delay in the wire and also the capacitance that actually exceed the gate delay. So the gate delay we have discussed in lab, okay, AND gate, NOR gate, and so on. That's actually the delay inside the gate, okay. So moreover, the wires are packed very closely. So that's actually the real situation, okay. Wires are packed very closely, okay. There's a large fraction of their capacitance is tunable. So actually, we will also introduce capacitance. Remember, we have discussed when two wires conducting current, okay, and then we have gap in between, and that's actually will create capacitance. So the C is not actually the actual C. We cannot see the capacitor. The capacitor is actually exists as a result of the two conducting element of this, like this one. Okay. So when one wire switches, this is actually it's one to relate to crosstalk, right? Crosstalk. So when one wire switches, it tends to affect its neighbor through capacitive coupling. So that's what we call as capacitive coupling. So we will see on this one, and the effect of MCF, Miller coupling factor. MCF. All right. So wires also account for a large portion of switching energy on a chip. So that's actually need to be considered very, very carefully by the designer. Okay? So switching energy of a chip relate to the low power design of a chip. So that's why we have discussed about how do we control the wire to a certain portion of block. So for example, we have discussed, we have 4 different operations, adder, subtractor, divider, or and multiplier, for example. Let's say we want to do the operation of adder, for example. So we don't use the other 3 blocks. So what we do, we disable the clock, okay, for the 3 different regions. Only we use the region that used for calculation of the addition just now. Okay. So to performing that one will reduce actually the switching energy on the 3 particular block. That's actually example. Okay, on-chip interconnect inductance has been negligible. So for this lecture or for this course, we will not discuss about the effect of inductance because it is negligible. Okay, however, it still have the effect lah. Okay, so remember you have learned about R resistance, R, L, inductance, and also C. So each of these got effects, okay, but in our lecture or in our course, we will focus more on this R and also this C element. Okay, that's why we call it RC delay. Okay, RC delay. All right. On-chip interconnect inductance, okay, we have covered this. So considering all these factors, circuit design is now as much about engineering the wires as a transistor that's underneath. It means that wire engineering is very, very important. We need to know detail about the wire engineering rather than other elements like transistors and so on. We still need to consider transistor, but the challenge is more on the wire. How do we interconnect them in today's technology? Okay. So chips are mostly made of wires called interconnect. So this is just what we call recall back what we have discussed just now. Okay. So what this line of sentence try to explain is actually most of element in our chip actually wires. Okay, most of the element, right? So in stick diagram, wires set side. So you have learned stick diagram. Okay, you have learned the stick diagram. So stick diagram actually will give us estimation on the complexity of our circuit, including the wires. Okay, we see the number of wires and how complex is it. Okay, and also the size of the chip we can estimate because wires set the size of the chip or the die. Transistors are little things under the wires. Okay. So many layers of wires. So we have many layers of wires. So I think if we go back, I think titanium processor, if I'm not mistaken. Under the previous one, we can see so we discussed this actually under physical design, the physical design. The physical design. Floor plan. Okay, under floor plan. Beginning of the chapter. I go and show to all of you about the complexity of the wiring. Okay, we have discussed this actually. Just to do recap. Okay. Chapter. Okay, plan. Chapter 1 or chapter 2. This is chapter 14. So we need to okay. So example of MIPS processor. So if you can see here is actually the schematic diagram. And what we interested on is actually on the layout, physical. Okay. Okay, here is a floor plan. We have discussed this, and then we see the complexity. For example, this one, a lot of wires as you can see from the top view of the chip. Okay, and then if you zoom in, okay, you can see here are all of these are actually wire that interconnect, and this is actually a complete chip. And when you zoom in at the different portion of the chip, you will see how complex is it. Okay. Right. Okay. So you can read on your own on this part. Okay. Right. Okay. So wires are as important as transistors. Okay, and that's why wires also is taken into consideration when we determine the speed, the power, and also the noise of a chip. Okay, we not only focus on transistor. Okay, we also focus on wires. Okay, because the wires determine the three elements of this. Okay, right. So how do we define wires in our chip? Here's actually the wire geometry. Okay. Let's imagine. So we have two wires here, the blue here, wire number 1 and wire number 2. Okay. How do we define the dimension of the wire? So first one they call pitch. So what is pitch? Pitch is actually the W, the width of the wire, plus S, the spacing between the wires. So that's what we call as pitch. This is important because we will use this as a reference when we discuss about the wire. Okay. Pitch, W, the width, and also the space. So aspect ratio, AR. How do we determine the aspect ratio? The aspect ratio is actually T divided by W. T over W. So T, what is T? So it's defined here. Actually the thickness of the wire. Okay. W is actually the bar, the width of the wire. So T over W, we will get AR or aspect ratio. So just look at this. All processes mean that the process before this long time ago, AR is lesser than 1. Means that it's too small. AR less than 1. But in modern processes, okay, AR is equivalent or almost equal to 2. So why do you think it's happened? It's happened because of, you just look at the equation. AR equal to T over W. So when for the old process, so T is actually smaller. T smaller. That gives the AR less than 1. Okay. But for the case of modern process, T is bigger than W. T bigger than W. When T is bigger than W, means that the thickness of the wire is bigger than the width of the wire. And then AR equal to almost 2. Okay, or what we call as skinny wires. Skinny wires. Skinny means that the width is what we call less than T. W, the width is less than the T. Width is less than the thickness of the wire for the modern process technology. So here is actually example. So we have 6 layers of chip. Okay. Let's see here. So we also have discussed this. Normally wires with M number 5 and M6, which is this one. So M5 and M6 normally is the thickest one, okay, thickest one. Why? Because we want to, transport. We want to distribute, okay, the VDD, the power supply, the ground supply, and also the clock to the chip. We want it to be thickest possible, so that lesser resistance, and that's why we can see here aspect ratio equal to 2. Okay, and you get T and you get W. T is more than the W. We can see here. So T 1720 divided by 860, you get 2. So in this case, you can see clearly T is bigger than W. So this is for layer number 6 and number 5. So imagine your lab. You can see clearly the size of your interconnect for your VDD, for your ground, for your clock is bigger. Okay, the thickest. compared to the other layers. Why we have multiple layers? Yeah, we want to support more complex design. That's why we have multiple layers. Okay, and also to deal with the complexity in the wire engineering. So some, for example, element. Okay, we have thickest size of wire, and some element thin size of the or narrow size of the wire, depending on the layer, and then that's actually wire engineering. We decide so which one need thickest, which one need narrow. Okay, so that's actually how do we decide. Okay, for this is actually typical. Typically, people or designer will use VDD ground and clock for thickest one. Okay, and then usually at layer number M5 and M6. And the thinner one, normally we go down to the substrate, thinner one, and closer to the our what we call our transistor, right? We call high density cells. Okay. So for longer wire, normally we use a thicker M2 and M2 until M4. So M2 until M4 is different. M2 until M4. So this is for longer wire. We want to we want to transfer the signal for longer area or longer destination. Normally we use for layer M2 and 4, right? So in terms of resistance, those with the thickest wires actually has the lowest resistance compared to those in the narrow and M1. So because M1 is actually closer to the our transistor sit very closely with, on the placement, and we don't need to have a longer wire to connect them. And this high density cell or area, we use a thinner or narrow interconnect, which it has a higher resistance compared to M5 and M6, but it's okay because it's not in longer distance, just a shorter distance compared to M2, M4, and then M5, M6. All right. So if you are asked to explain about this, that's the example, right? How do you explain? And you can refer to the textbook as well. Try to understand it and try to figure out after you have finished this section. Okay, this is actually the one that I'm actually planning to explain to you all just now. So we have figure A, okay, figure A, and figure B. Okay, so for figure A, 90 nanometer process technology and 45 nanometer process technology. Okay, you can see it clearly, figure A. Even you see the diagram here, this is thing taller than this one. Okay, but it's actually in terms of, this is just the diagram, but in terms of complexity, we can see the number of layers here, M8. It's actually M6. So 6 layers, and this 8 layers. Why it is 8 layers and why this one is 6 layers? Look at the process technology. The smaller the process technology, the more complicated we can what we call can implement in one chip, right? So this is, I think, the high-end process technology compared to this one, compared to A. Okay, so because B is 45 nanometer process technology. So in terms of wiring element, we need to have a lot of layers. In this case, we have 8 layers, or the 60 or 90. So for the 90 process technology, it has 6 layers. Okay, and we can see clearly here is actually our transistor at the very bottom one, same as this one. This is our transistors. All right. So if you have any question, you can ask me before we proceed to wire resistance.
Continue, sir.
Okay, thank you. So we have terms that we need to understand, okay, which is wire resistance. Okay, as we discussed wire resistance earlier. So how do we define the resistivity or the resistance of wires. So normally we use this equation. Okay. So R equal to rho. Okay, rho divided by T. T is the thickness of the wire. Okay. Rho is actually the resistivity. Resistivity normally we measure in ohm dot meter. Okay, ohm dot meter. Okay, dot meter. Okay, multiply with. Right, so divided by T. So rho divided by T is actually, maybe I use different color, the R square. Okay, the sheet resistance R square. And then the unit is ohm per square. It is actually no unit lah. Okay, for R square, no unit. Okay, so rho over T is actually R square, and then you multiply with the length of the wire divided by W. The length L here divided by the width of the wire, and then you will get the total resistance of the wire. Okay, so normally R square ni per unit resistance lah. You can imagine it's per unit resistance. And then to get the total resistance of the wires, okay, multiply with the length and also with the W. Okay, L over W. Okay, so count number of square R equal to, yeah, this is another way we can count the number of square. For example, this one we have 4 square, and to determine the total number of resistance, so R equal to R square multiply with the number of squares. So this is actually what we can see here. Choice of method. So we know that to try to transmit signal, okay, from one destination, so from a source to a destination, we need to have metal, okay, what we call as not insulator, metal, conductor. Okay, so different type of metal or conductor has different type of resistivity, different value of resistivity. For example, we can see here silver, for example. Silver, or in the equation of for silver is Ag, has 1.6 micro ohm per centimeter, dot centimeter. So that's actually the value of the rho resistivity. Okay, compared to gold, which is 2.2, and so on. So that's actually the resistivity value. So in this case, silver got very low resistivity value. Okay, and also copper as well. Right. So modern, until 180 nanometer generation, most wires were aluminium. So previously, most of the wires are aluminium. Okay, aluminium, which is this one. Okay, Al, and the value of the resistivity 2.8. Okay, modern processors use copper. Okay, copper. So copper less resistivity lah, which is 1.7. Okay, 1.7. So copper atoms are fused into silicon and they mesh fast. So that's actually the challenge lah. Okay, when you used copper or Cu here, okay, we have an issue of it diffuse into silicon, into our silicon lah, okay, and it will damage the transistors. So what we do, normally we surround it with diffusion barrier. So this is actually what they call as diffusion barrier to avoid from the diffusion into the silicon. All right. So in terms of sheet resistance, so R square sheet resistance for 180 nanometer process. Okay, normally this is actually the value lah. Okay, this is we don't have to memorize this. Okay, but you need to understand lah why the range is different. For example, metal number 1 until metal number 6, the range is in 0.0 something lah, 0.0x. And for diffusion and polysilicon, the value is a round number lah, round number, more than 1. You can see the category is different. Example, okay, we try to answer this. I give you about 3 minutes to answer this. It's very straightforward. You calculate the resistance, total resistance, to calculate the R. Use pen and paper. Try to answer this. I give you about 3 minutes. Okay, so what's the answer? R. So any response? Okay. So R equal to rho L, rho over, I think rho L. Just use rho T, rho over T, L over W. Rho T, L over W. Okay, so we just substitute the value of rho, which is this one. Okay, 2.2 divided by T. Well, what is actually the T? The thickness. So it's given here, the thickness of 0.22 micrometer. So the material used copper. I think copper, the value is not 2.2. The copper is 1.7. So it's not 2.2. So it's 1.7. Okay, 1.7. 10 to the power of minus is micro. So this 2 meter. All right, and then the T is 0.22. Okay, and then my suggestion, so this is micro. Okay, micro to the power of minus 6. Huh? So you can standardize it to make this as a minus 6 as well. Okay, so you make it as 220 lah. Okay, so we divided them together, and then you will get better. Okay, and then L, so the length is actually 1 millimeter or 1000 micrometer. Okay, and the width of the wire, okay, or the width of the wire is 0.125. It's very straightforward. You will get the value of R. Okay, how much the value of R? Any of you try? Can respond to this value of R. So that's actually the disadvantage of having online class. It's not easy to get response from the student. And if we go to the face-to-face, and then it's easier for me to get the response. Okay, there are pros and cons actually. I already looked at the response. Some of you wanted for hybrid mode. Okay. But next week, yes, we will do face-to-face. We will see it first. Okay, and then so that we can know each other. All right. So contact resistance, contact and vias also have. So this is actually typical value of resistance. 2 to 20 ohms. Okay. And these two diagrams shows how we reduce resistance. Normally they use this way. Okay. We use multiple contact to form low resistance connection. Okay. So when we have many small contact, okay, so this actually will increase the connectivity, or will give us low resistance connection. Right. Other than resistance, we also have the elements of capacitance. So that's actually the effects of C. This is actually what I discussed with you all. So here is actually wires at different layer. Okay, we see here layer N, and the top layer and the bottom layer. So top layer N plus 1, the bottom layer N minus 1. So in between here, we have layer N with 3 wires, 1, 2, and 3. So in between the wires, we have what we call as adjacent capacitance. So ADJ stands for adjacent. Adjacent ini bersebelahan lah. Okay, neighboring capacitance. So we have 2 neighboring capacitance, and that's why we have the equation 2 adjacent. Okay, and we have top and bottom, and that's why we have top and bottom. So this actually, the summation of this will give us C total. So that's how we calculate the C total, or total capacitance in the layer N. The layer N, we focus on layer N. Right, and then we also have other equation to calculate the capacitance value, which is C equal to sigma A divided by D, whereby A is I think the area and D is the distance. Sigma is we use a constant. Okay, wires are not parallel plates but obey trends. So they has a trend. Increasing area, okay, the width and also the thickness increases the capacitance. Okay. So if we make the area bigger, we will of course have a bigger capacitance. Okay. Increasing distance, this is the other way around. If we increase the distance, we will reduce the capacitance. But when we increase the distance, that's actually will requires more area of our chip. Okay, more area. So more area, normally we cannot have a better or bigger yield per silicon wafer, and that's actually the trade-off lah. That's why in wire or chip engineering is very important. We try to find the optimum. Okay, so dielectric constant, so sigma. So this is actually for your information. Sigma is equal to K multiplied with epsilon 0. So we need, I think, air permittivity 8.85. Okay, and then K depends on the material. So 3.9 for silicon dioxide. Okay, for your information, you don't have to worry about it. Okay, so wire model. So this is very important. Okay, for you to remember, to understand. Okay, so wires actually we can imagine wires as distributed system. Okay, so wires we can consider as distributed system. Okay, so we can do approximation, okay, or model of the wires with lump element model. So we just look at this one. So we have R and C because we have wires like this one. So inside the wire, we model it as a resistance, and in between the wire we have capacitor, right? And that's why you see the pattern of R and C. Okay, okay. R and C. Okay, and then these actually we can divide into n segment. So we just divide by n, R by n. So we will see the connection or the network of the lump element just now. So this is actually the lump element of this of the n segment. We lump them together, become R over R and C. Okay, so we also have 3 different models of wires. So look at the pattern or the shape. So we have L model, okay, like this one. We call L model because of the shape like L, like this one, L. Okay, R and C. And we also we can model the wire as pi model. See the pattern like pi in the shape, like pi shape. Okay, and we have T model. Okay, like a shape of T. Okay, so the value of capacitance and resistance is different depending on the shape. For example, R and C is solid, R and C, but for pi model, because C is divided into 2C, here, C here and the other C, and that's why we divide by 2. This is per segment for one segment. And in this case, we have 2 resistance here, and we divide by 2. Okay, towards the end, it contributes the same, actually, to the total R and C. So for 3 segment pi model, means that we repeat this. This is actually 1 segment. So for 3 segments, we repeat this 3 times. So it's accurate to 3% in simulation. Okay, L model needs 100 segments for same accuracy of the 3 segments. And that's why pi model is widely used to model the wiring. Okay, to model the wire element, to perform the wire engineering. So to get the same accuracy of the 3 segments, we need to have 100 segments for the L model. And that's why normally people use pi model. So use single pi model for L model. So you can see in the detail of this in the textbook. You go to the wastage and the Elmore delay. And in fact, for assignment, I think we have on delay as well. Yeah, delay model. Okay, delay model and their influence in overall system performance. So you can relate with the delay model. Okay, and can relate with the overall performance of the system. All right. Okay, example. Try to do this. I give you time to do this, and then we can continue. Okay, so we have metal 2 wires in 180 process. Okay, with 5 millimeter long. That's actually the panjang wire to 5 millimeter long, and the wide is 0.32. So we construct a 3 segment pi model. So we know that pi model. Okay, you go back here. This is the pi model. Okay, we have R. Okay, and we have C. This is 1 segment. 1 segment. So construct 3 segments, and then you get the value of R and value of C for the 3 segments. This is 1 segment. You make it 3 segments. and we shall discuss after this.
Saya nak tanya,
Yeah, okay. Proceed.
apa beza yang model-model tu ada tujuan lain-lain ke? Pi
Okay.
dengan TL semua tu.
Okay, thank you. So as discussed here, so normally, okay, we use pi model. Okay, designer use pi model lah. So but the other model is actually depending on the designer. Okay, so this is just to show the capability or the ability of performing modeling. Not only pi model, we can also perform L model and also T model. So in terms of practicality, most of the designer use pi model. Okay, the other model for your information. Okay, is that clear?
Okay sir, thank you.
Okay, all right, thank you. Is there any other question? If no question, can do example number 2. Right, so hope you already get the answer. So to get this, first you need to calculate the total resistance. What is R? So we have the value of R here, right? R and C. R and C. But in this case, we need to have 3 segments, so we repeat 3 times. So the C is actually different. Huh? So this is the second segment. Then we have another segment. Sorry about the drawing. Okay. Then we have another C here. So C altogether is actually 6. Huh? So C divided by 6. C divided by 6 for each of these. C divided by 6. C divided by 6. C divided by 6. And C divided by 6. So these are actually the segments. And R divided by 3. Divided by 3. So to get the value, we need to calculate the total resistance and total capacitance. R divided by 3. Okay. Any question on this? If you have question, just let me know. So in terms of segment, we can see clearly we have 3 segments. Segment number 1, number 2, and number 3. So to get R, okay, R equal to, so we'll go back to the definition of R. R equal to R square multiply with L over W. Okay. Whereby R square equal to rho over T. Okay. So R square multiply with L over W. Okay. So L is actually the length of the wire, which is 5,000 micrometer or 5 millimeter. So it's actually 5,000 micrometer, 5,000 micrometer. Why we use micro? Because we want to standardize the size, the unit. Okay. Right. So the width is actually 0.32 W, 0.32 micrometer. So you can cancel off the unit, and then R square. So R square is depending on the metal, type of metal. So in this case, metal 2. So metal 2, if you go back, resistance of metal 2, the sheet resistance is 0.05. You just substitute that, and then you will get the value of R equal to, make it bigger, equal to, I think, 781 ohms. Just check. If not, just like
781.25.
ya, 781. Kalau ada respon yang macam ni, online class pun okey. Tapi macam mana pun we need to have to feel like this one. See. Okay, 781.25 ohms. Okay. Then C, try to calculate C. Oh. And so C equal to C per micron. C per micron multiply with the length of the wire. That's normally we do. C per micron is 0.2 femtofarad. Okay, so that's actually the value. And multiply with 5,000 micrometer, and then you will get I think 1 picofarad, 1 pf, 1 picofarad. So C per micron normally given lah. Okay. 0.2 femtofarad, I think somewhere. This one. 0.2 femtofarad per micrometer. So this is actually typical wires punya capacitance. So when you substitute, so compared to gate capacitance, wire capacitance is 0.2. So gate capacitance 2 femto, and wire capacitance is actually the factor of 10 lower than the what we call the gate capacitance. So 0.2 femtofarad, okay, per micrometer, multiply with 5,000, then you will get 1 picofarad. Am I right?
Pico, yes.
Yeah, okay. So 1 picofarad or 1,000 femtofarad. Okay, so to get it for the each value of here, so you just divide by 6 lah. So we will get normally this equal to 167. Okay, 167 femtofarad. So that's actually the value of each resistant element in the 3-segment bimodal. And the value of each resistor here is actually, you divide it by 3, 781 divided by 3, you get roughly around 260 ohm each. 260 ohm. 160 ohms. That's actually the value of the resistance. Okay, so we have 3 resistors here. If you divide by 3, and then you will get around 260. Okay, any question before we proceed? Hopefully okay lah, everyone clear. Alright, so now Haris.
Kalau typical sheet resistance tu dalam exam ada bagi sheet resistance.
Yeah, alright. So normally, if you are asked in exam, you will be given the value lah. Or if not given, you use a typical value lah. Use a typical value, right?
Okay, sir.
Okay. Yeah. So talk to exam. So our exam is face to face. It's not online. Final exam is face to face. Right? Okay. So crosstalk. So crosstalk, or in Malay word they call cakap silang. Cakap silang is something like in electronic. Okay. I think this one already mentioned earlier. When we have 2 wires, okay, switching either from 1 to 0, okay, 1 to 0. This wire switching 1 to 0, okay, or 0 to 1, or 0 to 1, the switching. It tends to interrupt, so maybe I can use different color, different wires. Okay. Tend to interrupt the other wires. Maybe for example, use maybe this color. So we have this wire. So it tends to interrupt this wire. Okay, so that's actually due to the what we call as capacitive coupling. Capacitive coupling. What is capacitive coupling? So the capacitance effect in between the 2 wires. So remember, when we have the wire, 2 conducting wires at the top, at the bottom, and in between we have the gap, and it actually will introduce capacitance. Then due to this capacitance effect, and it will give us capacitive coupling, or sometimes they call as crosstalk. Okay, means that the adjacent wires or the neighboring wire tend to switch to. Is tend to switch to either we switch 1 to 0 or 0 to 1, dia pun will follow the switching value. Why it tends to switch to? Because the behavior of capacitor does not like to change its voltage instantaneously. Dia tak mau ubah, change the voltage. So that's actually a behavior of capacitor. So a wire has high capacitance to its neighbor, and that's why when the neighbor switches from 1 to 0, so let's say the green one is the neighbor, 1 to 0 or 0 to 1, the wires close to it, the neighboring wire, tend to do the switching too. Okay, to perform the same switching operation because of the effect of C. Yeah, that what we call as capacitive coupling, because a couple of two. Okay, and the effect of the crosstalk, it will give noise to the non-switching wires. For this case, it will give noise to this wire, okay, this yellow wire. Okay, and when we have noise, and it will increase the delay on the switching wires as well. Okay. Increase delay in the switching wire. Okay, how do we determine the effect of the crosstalk? Okay, normally we use what we call as Miller effect. Miller effect. So how Miller effect actually happen? Okay, how Miller effect happen? We use this table. Okay, all right. So we have this diagram. Just look at this diagram. We have two wires here, wire A and wire B. So in between the wires, as we discussed, there will be a capacitor. Capacitor, because of when we have two switching or conducting elements or wires, and in between it will introduce what we call as capacitance or capacitor, C adjacent. And in between the wire and also the ground, we have C capacitance, or called here is C GND or C ground. We have two because two wires. Okay, and the effect of the what we call capacitance effect when the A or B do switching, we see this table, MCF, Miller coupling factor, using MCF here. So the worst effect is actually number 2. The MCF equal to number 2. And the effective capacitance, we can see the total capacitance is actually C ground plus 2 C adjacent. C ground plus 2, double of this. So this is actually the very high effect. What happened when this happened? When switching opposite A. When B do switching opposite A. Means that when this B wires perform a switching opposite to A. So when A do switching, B do switching, and A do switching opposite of B. Okay, different direction. This is, for example, 0 to 1. 0 to 1. This is maybe 1 to 0. 1 to 0. So this will give different or bigger MCF value and bigger effect. As an engineer, we try to reduce the effect of this. Okay, right? And then the number of changes, voltage changes, is actually double VDD. The VDD multiply with 2 times the VDD. Okay, right. So the best one is actually MCF equal to 1. Normally MCF equal to 1. Okay, when MCF equal to MCF equal to 0. MCF equal to 0. Nothing happened on the changes of the voltage, and the effective capacitance only C ground. Okay, so when this is happen, when B switching with A, okay, B switching same as A, same value. Okay, all right. Any question before we proceed? So I think we will stop at the crosstalk noise. Then we will continue after. Wire generating repeaters. Not much lah. Okay, crosstalk control. And then after that we will finish lah. Okay. We try to do this exercise. Okay. So the question is, each wire in a pair of 1 millimeter line, 1 millimeter line or 1000 micrometer line has capacitance of 0.08 femtofarad per micrometer. So it's good to convert this to micrometer because our what we call value here given in micrometer. So the capacitance to ground, C ground is equal to 0.08 femtofarad per micrometer to ground, and C adjacent 0.12 femtofarad per micrometer. You notice that the C adjacent is bigger than the C ground. Okay, 0.12 and 0.08 to its neighbor. Each line is driven by an inverter with 1 kilo ohm effective resistance. Estimate the contamination and propagation delay. So I give you this as an exercise. Okay, you can do it on your own. Okay, we shall discuss in our face-to-face lecture next week. You will see how you settle this. Okay, any question before we end? I will stop the recording first.